Gravitational potential energy. In this video, we will discuss two important forms of energy. They are known as gravitational potential energy and elastic potential energy. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. If we lift an object, we do work. We are providing an upward force to overcome the downward force of gravity on the object. The force moves the object upwards, so the force is doing work. The work done on the mass is then mass times gravity times height. In this way, energy is transferred from us to the object. We lose energy and the object gains energy. If the object falls from that height, the same amount of work would have to be done by the force of gravity to bring it back to the Earth's surface. In other words, the work the force F did is recovered in the form of kinetic energy. This energy recovered when the object falls is known as gravitational potential energy. Gravitational potential energy is the energy a body has because of its position above the Earth's surface. The amount of gravitational potential energy gained by an object raised above ground level can be calculated using the equation. Gravitational potential energy is mass times gravity times height. Energy is in joules. Height is in meters. Mass is in kilogram. G is meters per second square or newtons per kilogram. Example. Calculate the gravitational potential energy of a 5 kilograms mass when it is 3 meters above the ground. Look at the figure. Take the formula and substitute the values given in the question. The gravitational potential energy is 150 joules. The following figure shows a roller coaster with a mass of 220 kilograms poised at point A. Calculate the gravitational potential energy at A with reference to the ground. The change in gravitational potential energy going from B to C. To find gravitational potential energy relative to the ground, we use that surface to define h equals 0 and make all height measurements from there. Replace mass with 220, gravity with 9.8 and height with 30 to perform the calculations. The gravitational potential energy relative to the ground is 64,680 joules. To find the change in gravitational potential energy from B to C, we make the gravitational potential energy at C minus the gravitational potential energy at B. In other words, the change in gravitational potential energy is mass times gravity times the change in height. The change in gravitational potential energy is minus 10,780 joules. The roller coaster loses 10,780 joules of gravitational potential energy between B and C. The second form of potential energy that we will discuss is elastic potential energy. Look at the diagram. Consider a horizontal spring whose left end is attached to a vertical wall. If we apply a force F to the other end, we will compress the spring. We are providing force to the left to overcome the spring force. The work done on the spring is then 1/2 times the spring constant times displacement squared. In this way, energy is transferred from us to the spring. We lose energy and the spring gains energy. We do work against the spring force, and that work ends up stored as elastic potential energy. The energy is stored until the force is removed and the spring back to its original shape, doing work in the process. Elastic potential energy. We call the energy in a deformed spring the elastic potential energy. The amount of elastic potential energy stored in the stretched spring is 1/2 times spring constant times displacement squared. Energy is in joules. K is in Newton per meter. Extension X is in meters. A spring has a force constant of 60 newtons per meter. The spring is extended by 5 centimeters. Calculate the elastic potential energy stored in the spring. Look at the figure. Take the formula and substitute the values given the question. A spring is stretched to a position 35 centimeters from its equilibrium position. At that point, the force exerted on the spring is 10.5 newtons. What is the elastic potential energy stored in the spring? To find the elastic potential energy stored in the spring, we first calculate the value for K, the elastic constant for the spring, using Hooke's law. We now use the formula for the elastic potential energy to find the elastic potential energy for a stretch of 0.35 meter. The energy stored in the spring at the initial stretch is 1.84 joules. If the stretch in the spring is allowed to reduce to 20 centimeters, what is the change in the elastic potential energy? To find the change in the elastic potential energy, first find the elastic potential energy at a stretch of 0.2 meters. Then subtract from that value the answer to part A. The elastic potential energy for a stretch of 0.2 meters is 0.6 joules. The change in elastic potential energy is minus 1.24 joules. The spring loses 1.24 joules of elastic potential energy between the points 1 and 2. Now, after discussing the potential energies, we should notice some similarities between them. We now pay attention to the second example of the gravitational potential energy. We know that the work done by a constant force on an object is defined as the product of the component of the force along the direction of displacement and the magnitude of the displacement. So, the work done by weight from B to C is positive because the force and the displacement are in the same direction. The work done by weight is 10,780 joules. We should note the value is negative of gravitational potential energy change. We now pay attention to the second example of the elastic potential energy. The work done by spring force from position 1 to position 2 is positive because the force and the displacement are in the same direction, and the work is equal to the area under the curve. We should note this value is negative of elastic potential energy change. The work done by some forces, such as weight and spring, have special characteristics. The work done by them depends on the starting and ending points of the motion and not on the path taken. We do work against these forces and energy is stored. This stored energy is recoverable as work, and the change in a potential energy can be defined as being equal to the negative work done by the force. Gravitational force and spring force are two such examples of conservative forces. Any force that meets these characteristics is called a conservative force. Let us summarize. Conservative forces have the following properties. The force only depends on the initial and final position, not on the path between them. The work done by a conservative force is reversible. A conservative force results in potential energy. The work done by the force conservative equals the negative change in potential energy. Gravity force is a conservative force. Spring force is another conservative force.